And we're back to conclude 18-2 where we're dealing with equilibrium. And I just realized that in the previous podcast we told you to try example number 6 and example number 7, and you don't have the data for this. So let me go ahead and give you the data for it. If you want to pause this, you can do that. In this question, it says, consider the combustion of ammonia. We've actually done this reaction in example number 3, or did this reaction in example number 3. And it says to calculate the KEQ if the compounds have the following concentrations at equilibrium. So let's go ahead and give you those values. Let's say that the ammonia has a concentration of 1.25 molar. Let's say that the oxygen has a concentration of 0.50 molar. We'll say that the NO2 has a concentration of 3.25 molar, and the concentration of the water will be 4.00 molar. So now you have enough information to solve and answer example number 6. And scrolling down here, we'll go ahead and give you the question. Go ahead and calculate the let's say the oxygen concentration. That's what we're going to look for if the following concentrations are found at equilibrium. So we'll say that our ammonia is 0.10 molar. We'll say that the NO2 is going to be 0.75 molar. And we'll say that the water is going to be at 1.10 molar. So if you want to pause this podcast and solve those, feel free, and we'll be going over those answers during the rest of this podcast. Okay, so in example number 6, we need to solve for KEQ. In example number 3, we determined that KEQ is going to equal, let's go ahead and get our denominator line here, is going to equal the nitrogen, the NO2 concentration raised to the 4th times the water raised to the 6th divided by the ammonia raised to the 4th, and the oxygen raised to the 7th. And now all we need to do is plug in our equilibrium concentrations and solve for KEQ. So that's going to be 0.325 raised to the 4th times our 4.00 raised to the 6th divided by our ammonia, which is 1.25, which is raised to the 4th, and our oxygen is 0.50 raised to the 7th. And all you need to do is evaluate that. Again, in some cases, if you want to do this in multiple steps, you can. You can put parentheses around the entire numerator, parentheses around the entire denominator. However you prefer to solve this is perfectly fine. And that's going to give a value of 2.40 times 10 to the 7th. So this is an incredibly large KEQ, and so this would suggest that the reaction lies far to the right. Now, in example number 7, we now know what KEQ is from the previous example for this expression. Now we want to solve for our oxygen. So we use the same equation, KEQ. I'm just going to keep everything in black in this case. KEQ will equal the NO2 raised to the 4th, the water raised to the 6th, the ammonia raised to the 4th, and the oxygen raised to the 7th. Now there's different ways that you can solve for this. You can plug in all the numbers as we've done previously and then solve for the oxygen, or what you can do right now is rearrange the equation to have the oxygen isolated. So let's go ahead and try that just to show you a different way of solving these. I'm going to go ahead and multiply both sides by the oxygen raised to the 7th power. Alright, so now the oxygens divide out on the right hand side. I'm going to divide both sides by KEQ. So now my KEQ is out of that part of the expression. And so now what I'm left with is oxygen raised to the 7th power equals the NO2 raised to the 4th, the water raised to the 6th, the ammonia raised to the 4th, get rid of that there, and KEQ is also in the denominator. And now the last thing I would do to solve for the oxygen is I would raise both sides to the 1/7 power. Take this whole thing to the 1/7 power. And so now what I'm left with is the oxygen concentration equals NO2 to the 4th, water to the 6th, divided by ammonia raised to the 4th, KEQ, and the entire term there raised to the 1/7 power. And so now I can plug in all of my values. So scrolling back up here, my NO2 is 0.75. Go ahead and put that in orange here. So I do have my 0.75 raised to the 4th. My water, 1.10 raised to the 6th, divided by the ammonia is 0.10 raised to the 4th, and my KEQ comes from the last question. KEQ is right here for this expression, 2.4 times 10 to the 7th. And that entire thing is going to be raised to the 1/7 power. And when I evaluate that, I do get 0.303 molar oxygen. That would be the oxygen concentration if the ammonia is 0.1, the NO2 is 0.75, and the water is 1.1 molar respectively. Alright? Now if you would like, you can plug this value back in with the other three back into the equilibrium expression and make sure that you do come up with your equilibrium constant K. That concludes 18-2.